Hello again. In the previous video, we saw some examples of indefinite integrals using U substitution. Here are three examples of definite integrals. So I'm going to show you two different styles of doing this. First, let's treat this as indefinite integral. So we're just finding antiderivative of the given function, and then once we have that antiderivative, then we use the fundamental theorem by plugging in the upper limit and then minus plugging in the lower limit. So this one, we know derivative of tangent is secant squared x. Derivative of tangent x is secant squared x. So therefore, this part, secant squared times dx, we want that to be the du. So that's du. And therefore, u would be tangent x. So now let's write du below it. Derivative of tangent x is secant squared x, and du would be secant squared times dx. So this is the differential of that function, which is the derivative times dx. So now let's make the substitutions. So then this is the integral of tangent cubed tangent cubed of x, which is u cubed, right? The tangent is u, and the secant squared times dx is the du. So now the new integral is u cubed du, and that has antiderivative by power rule, which is 1/4 u to the 4th plus c. And now plug in the u in terms of x, so that gives you tangent to the 4th of x plus c. This is one way where you ignore the limits first, find antiderivative. Now we want to apply those limits. So let me rewrite the integral. So this is the integral from minus pi over 4 to pi over 4 of secant squared x times tangent cube x dx. So this was the original question, but we ignored the limits. We did the antiderivative first. Now that we have the antiderivative, we don't need to use a c. So this would be the function 1/4 tangent to the 4th x evaluated at the endpoints, and you subtract. So the next step is to plug in pi over 4 and minus pi over 4. So this is 1/4 tangent to the 4th of pi over 4 minus 1/4 tangent to the 4th of minus pi over 4. And that's equal to 1/4. Tangent of pi over 4 is 1. So this is 1 raised to the 4th power, which is still 1, minus 1/4. Tangent of minus pi over 4 is minus 1. So this is minus 1 to the 4th. And they both give you positive values, but you're subtracting. So 1/4 minus 1/4, which is 0. So that integral, the final answer is 0. So that is. Also, you may see sometimes by symmetry, especially when the interval over which you're integrating is symmetrical, as well as the function being an even function, then I mean the odd function, they cancel each other out. On one side you have the function either above the x-axis and on the other side below, or the opposite, so that geometrically you may be able to see sometimes when it's zero. But here the point was to demonstrate the two different ways of finding antiderivatives. So here's the finding the integral. Here's the second way. So I need more space. Okay, so this is another way. So let me start with that integral. Let's say we don't check for symmetry and we don't find the answer. So this is something in general you can do. And we did the u substitution. So I'm going to do it again. U is tangent x, du is secant squared x dx, and then when we set this up, we continue in the same line. So this is equal to finding the antiderivative. First of all, do the substitution and then find the antiderivative. So now when you put this, I'm going to put the limits in a moment. First, let's substitute the inside the integral. Secant squared dx is du, so that will be du at the end. And then tangent cube is u cubed, so we have u cubed du. Now, when you set this integral in terms of u, then the lower limit and the upper limits should be values of u. The original one are values of x. When x is pi over 4, u is tangent of pi over 4. Which is 1. And when x is minus pi over 4, u is tangent of minus pi over 4, and which is negative 1. So now when you find antiderivative, you get 1/4 u to the 4 again, but this time you don't change u back to tangent x, you just plug in these new values, negative 1 and 1. So that gives you 1/4 1 to the 4 minus 1/4 negative 1 to the 4. And then again, you get 0. So these are two different styles of treating definite integrals with a u substitution. So let's try another example. In this example, I'm going to choose u square root of x. Then du, there's no written book that tells you exactly what you should be in every situation, on every problem. So it all depends on the problem. The only way to learn this is by practice. So if you take a variety of problems like this, try different kinds of u substitutions. Some of them may work, some may not work. You want to learn this by practicing. So if u is the square root of x, then du would be 1/2 square root of x dx. And now in the denominator, we don't have a 2. So if we put a 2 in the denominator here, then I have to put a 2 in the outside. So 2 divided by 2 is 1. So that doesn't change. And then this becomes 2 times integral. Now these values, these limit values belong to x. So I want to use u here, like the last example. So when x is 1, u is the square root of 1, which is 1. When x is 4, u is square root of 4, which is 2. So now the new limits of 1 to 2. And then inside integral, I have e to the square root of x, which is u, e to the u. And then the other part, this part here, this part is just du. So we have e to the u du. And that's equal to 2 times antiderivative of e to the u is e to the u. Now here we don't need to change u back to square root of x because the limits of integration already take that into account. So then we have integral from 1 to 2. We evaluated at 2 and at 1. So you get 2e squared minus 2e to the first power is just 2e. And that is the value of that integral. So you just feel whatever you feel comfortable with, this way or the first way that I did, like this one, I just ignored. But make sure when you do that, you have to open a new line. You can't just continue there, because if you just continue changing to u and then you still keep the original, then the new limit, the new integral is not equal to that. Even if you later change u to whatever u was substituted for, you still, the equalities don't make any sense. They're not equalities. So that, you may get the final answer correctly, but in the middle, what you're saying is equal to the other is not really true. So now let's look at one more example. So here, integral from 1 to e of ln to the 5th power of x over x dx. So here I'm going to let u be ln of x. And the reason for this, because I know derivative of ln of x is 1 over x, and that's where 1 over x is. By the way, not every integration problem is doable this way. Only if it's set up in this way, it would work. It's if I change these expressions, I can make it impossible, really. So du here is 1 over x dx. So then this equals, and so you can see this du 1 over x dx, that's the du. So we have integral. First, let me change the limits. When x is 1, u is ln of 1, which we know it's 0. When x is e, u is ln of e, which is 1. And then inside you have ln of x raised to the 5th power. So that's u to the 5th power times the rest is just du. And now find antiderivative, which is 1/6 u to the 6th power. from 0 to 1. Plug in 1, you get 1/6 minus plug in 0, you get 0, so it's just 1/6 is the final answer. And this concludes the video.